All the millions of compounds we know today are composed of atoms of just a few elements, approximately 100. Now let's look at how we describe the composition and structure of chemical substances. We'll start with the chemical formula. The chemical formula of a substance is a notation using atomic symbols with subscripts to convey the relative proportions of atoms of the different elements in the substance. How many of each atom is needed to make up a substance is represented in the chemical formula. Aluminum oxide, Al subscript 2, oxygen subscript 3. Basically tells us there's 2 aluminum atoms for every 3 oxygens. This is the ratio, so 2 to 3 ratio. Sodium chloride, there's a 1-to-1 ratio between the atoms of sodium and chloride in sodium chloride. Calcium nitrate. We can look at this in terms of a ratio of 1 calcium for every 2 nitrates, nitrate being a polyatomic ion, which we discuss later on. Or we can look at it on an atom basis and say that in this particular substance, there's 1 calcium to 2 nitrogens to 6 oxygens. We have some terminologies associated with chemical formulas that depend on the bond type as to what terminology we use. For molecular substances, it involves covalent bonds. A covalent bond is something that shares electrons between atoms. Typically, this occurs with a nonmetal and nonmetal. Not always, but typically, generality. What we're saying here is that electrons are basically shared between atoms. That's a covalent bond. An ionic substance involves an ionic bond. That's where we have a transfer of electrons between atoms. There's an attraction between the charged particles. This typically occurs with metals and nonmetals or polyatomic ions. So you have one species giving up electrons, something else taking on electrons, so you end up getting charged species, and it is the attraction of those charges that is the actual ionic bond. Well, we have different terminologies as we talk things that are molecular versus ionic. Let's talk about molecular first. A molecule is a definite group of atoms that are chemically bonded together through sharing of electrons, covalent bonding, generally a non-metal, including hydrogen. We refer to these substances as molecular substances. It is a substance that is composed of molecules, all of which are alike. It takes billions of molecules of a species to make up that species that we see. A molecular formula gives the exact number of atoms and elements in a molecule. Okay, so if we're talking about a molecular substance, we have molecules and we have a molecular formula. Example, ethanol has 2 carbons, 6 hydrogens, and 1 oxygen. Now sometimes we have something called a structure formula that gives more detail of how the atoms are bonded to one another in the molecule. Take that methanol, the ethanol, the C2H6O. We could write a structure formula in the sense that we have CH3, CH2OH. This tells me I have 3 hydrogens attached to carbon. That carbon is attached to another carbon which has 2 hydrogens attached. And we have an oxygen attached to that carbon, and then a hydrogen attached to that oxygen. In essence, we're looking at as a structure formula. This is something that you'll come across in our course a little bit, but you get a lot more detail of that when you go to organic chemistry. Let's talk about ionic substances. Although many substances are molecular, others are composed of ions, in other words, charged particles that have transferred electrons and have ionic bonding. Occurs generally with your metal-non-metal interactions. An ion is an electrically charged particle obtained from an atom or chemically bonded group of atoms by adding or removing electrons. So we talk about sodium and chlorine. Sodium can give up an electron, chlorine can take it on, so that we end up having 1 less electron in your sodium, so it's positively charged. Chlorine would have an extra electron compared to its number of protons, so it's negatively charged. Those charged species are referred to as ions. Okay, they are ions. Sodium chloride is a substance made up of ions. So basically you have ionic bond where the positive charge and the negative charge are attracted to each other and forming that ionic bond in that species. The ratio of atoms in an ionic compound is displayed in something called the formula. Formula of ionic compound is written by giving the smallest possible whole number ratio of different ions in the substance. This is comparable to the molecular formula for molecular substances. The formula unit of a substance is a group of atoms or ions explicitly symbolized by its formula. Comparable to the term molecules, where we're talking about molecular substances. So in summary, covalent bond is a sharing electrons. It's typically a non-metal. An ionic bond is transfer of electrons, attraction of charged particles, which is typically a metal-non-metal, and charged ions. We refer to molecules in covalent bonded substances. We refer to formula unit. An ionic bond. Refer to it as a molecular substance in covalent bond, ionic substance, ionic bond. Refer to it as molecular formula, covalent bond, formula when we're dealing with ionic bond. So for covalent bonding, there's a sharing of electrons. Got a pair of electrons between two atoms, and they equally share, or not necessarily equally sharing, but they're sharing the electrons between the two species. And I have charged species, the attraction between the charged particles in ionic bond. When an atom gains extra electrons, becomes negatively charged, we refer to that ion as an anion. Has more electrons and protons. So the Cl minus, that's the chloride anion. Atom that loses electrons becomes positively charged is called a cation, more protons and electrons. So sodium plus is referred to as a cation. An ionic compound is a compound composed of cations and anions. Answer the following questions for species below. Basically, we're trying to take those definitions we just learned and apply into these substances. I want to know if it's ionic or molecular substance. Is it a formula union or a molecule? Does it have ionic or covalent bonds involved? Looks like it's sodium chloride. What we're talking about here is a metal and a non-metal, if you look at the periodic table. So therefore, since it's a metal and a non-metal, we must be talking about an ionic substance. Since it's an ionic substance, do we refer to sodium chloride as a molecule or a formula unit? That would be a formula unit because it's an ionic substance. And then what kind of bonding is it? Well, it's a metal-non-metal, therefore it's an ionic bond. Let's look at CaBr2, calcium bromide. Once again, we're talking about a metal-non-metal, so we're referring to an ionic substance. We will refer to this as a formula unit, because it's an ionic substance, and we also have ionic bonds. Sodium sulfate. This is an interesting one because it involves that SO4, which is a polyatomic ion, something we're going to cover later. But that SO4 is a species by itself. It's an ion, okay, and it has non-metal and non-metal, so that in itself has covalent bonding in it. But it's a charged species, so it's going to be attracted to that sodium plus, okay, which is ionic bonding. So it has both ionic as well as covalent bonding. It's an ionic substance because it's two atoms attracted by charges. And it's going to refer to as a formula unit, but it will have ionic bonds as well as covalent bonds. The ionic bond will be the sodium and sulfate attracted, and then they also have the covalent inside the sulfate ion. CO2, carbon dioxide. This is a non-metal, so this is a molecular substance. Since it's a molecular substance, we would refer to this as a molecule. And it has the non-metal bonding, so therefore we're talking about covalent bonds. Another important topic dealing with terminology and being ionic or covalent, etc., has to do with things, ions in aqueous solutions. Many, not all, ionic compounds, ionic bond, metal, non-metal, dissociate into independent ions when dissolved in water. If a species is considered soluble, and we'll get to which species are soluble or not, but if it's considered soluble, then what we're saying is it's an ionic compound that breaks up into its ions. Okay, soluble ionic compounds associate 100%, referred to as strong electrolytes. They break into their charged particles until it reaches its saturation point. Saturation point means as much as it can get in solution before it starts precipitating out as a solid. It's not infinity. There's some limit to the species. Some species have higher saturation points than others. Sodium chloride has a high saturation point. We can get about 36 grams of sodium chloride in 100 milliliters of water. But once it reaches that point, any more that we put in there will come out as a solid. That's not going to go in solution anymore. It's reached its saturation point. So sodium chloride breaks up into charged particles. I have sodium ions and chlorine ions. And this is because this is a soluble ionic compound. Insoluble ionic compounds do not break up into ions, or not to any appreciable amount. Another topic that we'll cover later on. Most molecular covalent bond non-metal compounds dissolve but do not dissociate into ions. The only exception to this is the acids. Your acids tend to ionize when they go into aqueous solutions. So we're looking here at glucose. It's soluble, which means it will go into water, but it does not break into 6 carbons, 12 hydrogens, and 6 oxygens. It stays as a whole molecule. Okay, it stays as a whole molecule. These compounds are referred to non-electrolytes. There are no charged particles. They're soluble to their saturation point, but there's no ions formed. No charged particles. It remains whole. It stays as a whole compound. Now, if you're following what I'm saying here, you should be able to answer the following question. How would sodium sulfate dissolve based on bonding? Remember, we talked about sulfate, and we said that's a polyatomic ion that has covalent bonding. So we're saying that this is a soluble salt. Sodium sulfate is a soluble salt. If I stick it in water, it's going to dissolve to some point where it reaches its saturation point. The only thing that's going to dissolve then is those ionic bonds. Covalent bonds will not, okay, as demonstrated in our glucose example above. So what we're saying here is that sodium ion and that sulfate ion bond is going to dissolve, breaking into ions. So what's going to happen is we'll find 2 sodium ions and 1 sulfate ions. The AQ behind it symbolizes that there's ions in solution. The ionic bond dissociates while the covalent bonds and sulfate remains intact. This is important concepts and definitions you need to understand as we move on later on in other sections in this semester. Ionic compounds. Most ionic compounds contain the metal and non-metal, as well as polyatomic ions. For example, sodium chloride. You name ionic compound by giving the name of the cation first, followed by the name of the anion with IDE. Some simple examples. Sodium chloride. Well, Na is sodium. We name it the name of the atom, which is sodium. Cl is chlorine. We take that INE and change it to IDE, so you get sodium chloride. Calcium iodide, take the INE on iodine and change it to iodide. Potassium bromide, same thing. Use potassium the way it is, the name of the atom, and then bromide, we change to bromide. We'll give the monoatomic ion name for the cations and anions when naming compounds. So a monatomic ion is an ion formed from a single atom. So there's certain names. Typically it's the name of that species for the cations, for the metals. And then for the anions we tend to have the IDE ending on it. important question comes up is how do we get the charges for ions? How do I know that sodium's +1 and chlorine's -1? Calcium's +2, etc. Notice, if we go back, notice for calcium I had 1 calcium, but I have two iodides. Okay, why is it for this I have 2 to 1, while in sodium chloride I got a 1 to 1, and potassium bromide I have a 1 to 1. Well, it has to do with the charges. Okay, calcium has a +2 charge, iodine has a -1, so I'm going to need 2 of those to balance out that formula. So the rules for predicting charges on monatomic ions. Most of the main group metals form cations with the charge equal to their Roman group number. You remember the periodic table and had Roman numerals on it. So what we're saying is Roman numeral 1 here is going to end up having a +1 charge. Roman numeral 2, +2. Roman numeral 3, 3+. Roman numeral 4, 4+. What's going on here is a transfer of electrons. What it's doing is trying to get to an octet where it has 8 electrons around its valence shell. So it's easier for them to lose electrons to get to that arrangement than it is to gain. However, when we get to the further right of the periodic table, they only need to take on a few electrons to get an octet on the outer shell. So it's easier for them to take on electrons than to lose them. So the opposite trend happens from the right side of the periodic table. We have our group 8, which has 8 electrons in it. So basically it has typical trend here is that the charge of the monatomic anion for the metal equals the Roman numeral -8. So group 8, you have 0. 7, you have -1. 6, -2. 5, -3. And 4, -4. So in this area right here, it kind of depends what the species is attached to, whether it's going to be an anion or a cation. Most transition elements form more than one ion, each with a different charge. So there's several oxidation states. Some exceptions. Cadmium is always +2, zinc +2, silver +1. There is a rare form of silver 2, but for the most part we claim that it's just silver plus. So you have your transition metals in this area here, which tend to vary. Which means it's very important then, as you're giving out the names of these species with the transition metals, to tell what is the oxidation state. Otherwise you cannot determine the formula. So when we write the name, we have to tell the oxidation state for these with the variable oxidation states. We'll do not for the ones that are always a certain oxidation state. Some other important elements with variable charges that you should be familiar with is lead 4, lead 2, tin 4, tin 2, arsenic 5, arsenic 3, antimony 5, antimony 3. These are also used sometimes with the older naming system, the ik and us, which we'll talk about on the next slide. Monatomic cations are named after the element. So if you got aluminum 3+, then you basically would call it aluminum ion. And we have ion there if it's just an ion. If it's part of a formula, we drop the ion name. So for sodium, it would be sodium ion. Calcium, calcium ion. Notice I do not have any charges there in the name because sodium is always +1, calcium is always +2, and aluminum is always +3. But something, remember we talked about those transition elements, they tend to have variable oxidation states. If there is more than one cation of an element charge, a Roman numeral in parentheses denoting the charge on the ion is used. This often occurs in our transition elements. So if we talk about iron, iron could be iron 2 or iron 3. If I just say iron ion, I have no idea what the charge is. So I have to give the Roman numeral. So I have to state what is the charge when I'm writing the transition metals. That way we know what is the oxidation state. When we write the formula, we know how to write it. As I mentioned, there was an older naming system that you got to be familiar with, where we have to have two oxidation states. The higher oxidation state, we use the Latin name and ik at the end of the name, or the lower oxidation state, we use the Latin name and the us. Example, iron 3 and iron 2. Iron 3 is the higher oxidation state, so we can call it ferric ion. Iron 2 is the low oxidation state, so we call it ferrous ion. Do the same thing with copper. You have copper, we can call it cupric ion for copper 2, and copper 1, cuprous ion. Mercury, Mercuric ion is mercury 2 plus, and mercurous ion is mercury 2, subscript 2 plus. If you look at it, that means this is mercury 1 plus. There's two of them, giving a total 2 plus. Sometimes some errors happening. This mercury subscript 2 plus is mercurous ion, mercury 1 ion. You also got to remember those other substances I told you to remember. Lead 4, lead 2, tin, arsenic, and antimony. These are ones that could be using the ic and us names with the Latin version of the names. For names of monoatomic anions, we use the stem of the name followed by IDE. For example, bromide. We drop the INE and we add IDE and call it the bromide ion. This is where we got the names for our substances we did earlier. Sodium chloride, calcium iodide, potassium bromide. A formula of an ionic compound is written by giving the smallest possible whole number ratio of different ions. That's important. It's the smallest whole number ratio. So you got to make sure that that's the case when you're writing the formula. Based on the charge of the ion and balance in the overall charge of the compound, by adjusting the number of ions, a formula is written. Note that the sum of all the charges must equal 0. And you do not display the charges in the final formula. So you have charges of the ions. You have to make sure that you balance out that the total charges equal the cation and the anion are equal pluses and minuses, neutral species at that point. Example, sodium chloride. We know that sodium is a +1 and chloride is a -1, looking at the periodic table and its location. So I know that this is balanced. I have one positive and one negative, so then my actual formula then would just be 1 sodium and 1 chlorine. So the formula is NaCl. Let's look at iron 3 sulfate. Ion charges. Well, iron is a transition metal, so I need to know what is the charge. Well, that's what's given to me by that Roman numeral 3. That's why it's part of the name. It tells me the charge. And sulfate, something that we're going to memorize as an ion, polyatomic ion, is SO4 with a 2- charge. Well, I have 3 pluses and 2 minuses. That's not balanced. I need to have the same number of pluses as I do minuses. Well, generally, you can crisscross the charge of one ion as the subscript on the second one, reducing when it's possible. Got to make sure it's the smallest whole number ratio. Okay. So what we're saying here is, okay, I got a 2 number on my sulfate, bring that down. My 3 on my iron, bring that over. So that's telling me now I will have 2 iron 3s, 2 times 3 plus is 6 plus, and 3 sulfates, 3 times 2 minus is 6 minus. That's balanced. Total of 6 pluses and 6 minus, which means my formula then is iron subscript 2, open parentheses, SO4, close parentheses 3. It's important to put the parentheses because I got to inform in the formula that we have 3 sulfates in that formula. 3 sulfates with a -2 charge. Chromium 3 oxide. Once again, Roman numerals telling me my charge on my chromium. I need to write my formula so I can crisscross and basically say I need 2 chromiums and 3 oxygens, which would give me a total of 6 pluses and 6 minuses. My formula is Cr subscript 2O3. Calcium nitrate. Calcium is always a +2. It's in that second column. Nitrate's a memorized polyatomic ion, which has a -1. So if I crisscross this, I'm going to see I need calcium, open parentheses, NO3, close parentheses, subscript 2. Sodium phosphate. Polyatomic ion, PO4 3-, memorized. Sodium plus, group 1, +1 charge. It's going to need 3 sodiums to every 1 phosphate, and a subscript 3, PO4. Strontium oxide. Strontium is a 2+, oxygen's a 2-. Now this is where the crisscross runs into problems. If I was to crisscross this, I would have SR2, subscript 2, oxygen subscript 2. I want whole number ratios. Those are both divisible by 2, so it goes back to your CRO, if you did the crisscross. I mean, obviously you can see you got 2 plus 2 minus, that's balanced. I just need one of each. Homework 13 and 14.